Hi 213. In this video we're going to finish section 11.3 by discussing symmetries. So we say mathematically a geometric figure has a line of symmetry, we denote that with a curled L here, lowercase l in cursive, if it is its own image under a reflection in or through line L. So each of these blue dashed lines here in this first figure are considered lines of symmetry because if you were to fold the figure across that line of symmetry there, you would have a perfect match on the other side. It's a line, it's a mirrored reflection across that line. It's perhaps easiest to see for this vertical line of symmetry here. If you were to fold the figure across this vertical blue line here, you would notice that these two sides completely match up with each other. So this figure actually has three lines of symmetry. In part B here, we notice that this figure here, which is a kite, actually just has one line of symmetry running horizontally here. Notice folding it across that will be a complete matchup, right? It's a reflection across or in that line. Here, the star, we have lots of lines of symmetry here because we're able to fold not only sort of through the tip here, right, but through these open spaces here, which coordinate to a tip on the other side, right? So we've got lots of lines of symmetry for this one. But other images have lines of symmetry, things that are found in real life. So for example, a ship here, now of course usually ships have little antennas and stuff on them, so that would make it different, but in general we say that this ship has a line of symmetry here cutting right through vertically right down the middle. If you want to think of it like that way, the two sides would match up. So let's see if we can determine how many lines of symmetry some of these examples have here. So let me maybe do some drawing for you here. So I think we could all agree that that this would be a line of symmetry down through here. Yes, pretend that's a perfectly straight line. Also here would be a line of symmetry, and here also. Any others? I think maybe vertically here. Yes. And then also there's more, right? So going diagonally this way and diagonally this way, right? And we could count them all up. We'll count those in a second. Let's see about this one. I think just down the middle. Correct? Yes. This one, a line of symmetry would be to cut it down this way, but also horizontally, yes, because we could fold it that way as well. This one, I don't see that there's a way I could actually draw a line so that when I folded the two pieces or tried to do a reflection across that line, they would completely match up. So let's see if we were correct. Yep, here we got 6, right, and all of ours matched up. Here we have 1, 2 lines of symmetry, and none. So there's not just line symmetry, there's also what's called rotational or turn symmetry, and we say a figure has rotational symmetry or turn symmetry when the figure can be rotated less than 360 degrees, so less than a full rotation about some point called the turn center, so it matches the original figure. So for example here, notice that in this triangle, we are able to turn the triangle so that if we turn it 120 degrees, remember that's going, we're assuming we're going this way, I guess, 120 degrees, that we will completely have the triangle looking exactly the same if we rotate 120 degrees, right? So let's look at this figure over here. I actually created a little animation so you can see how this works. So we're going to rotate it, and we're going to see if rotation allows us to produce the exact same figure, if it would have looked exactly the same. So let's see. That is rotating it 120 degrees. And that's rotating in another 120 degrees. So what we just noticed is that we have a turn symmetry here for both of these figures, and we actually were able to see it with this one with the turning, and we turned it 120 degrees. And so what we do is we say that the triangle and this other shape here have 120 degree turn symmetry. That's how we would denote that. We say they have 120 degree turn symmetry. But if we notice that we rotated the figure another 120 degrees, we find that it again matches the original. So what we can say is the triangle or the other shape over here also has 240 degree turn symmetry. So we could do 120 degree, but we could also do 2 rotations and get 240 degree turn symmetry. So quite honestly, we should label this very carefully because this figure here denotes doing rotation in a clockwise way, which actually for angle measurements, remember, is considered to be a negative angle measurement. So turns counterclockwise are considered positive, remember, while turns counterclockwise are considered negative. So as they've labeled it here, that's actually a negative 120 degrees, right? So rotating it this other way, the counterclockwise way, is considered positive, remember. So rotation counterclockwise is a positive rotation, positive degree measure. So let's see if we can figure for each of these what kind of rotational symmetry we have, if we have any. So notice in this shape here, it looks like because it's a regular polygon on the outside, that we would have some kind of rotational symmetry. So let's see what happens if we try. Ah, that looks the same, and we turned it a fifth of the way, didn't we? Yes, because there are 1, 2, 3, 4, 5 sides. We turned it a fifth of a full rotation. So what is a fifth of a full rotation? Well, we know a full rotation is 360 degrees, and so a fifth of that would be 72. Yes, so here we notice that if we go 72 degrees, we arrive at the same shape. That's what just happened in the animation. It rotated a fifth of a full rotation. So we have 72-degree turn symmetry, but notice that since it's a regular polygon, we actually have multiples of that, right? So we could go 72 or 144 or 216 or 288, right? So those are all of the possible rotations less than a full rotation that would produce the exact same figure. Okay, let's think about this one for a second. So we notice that we have, let's see, there is some kind of rotational symmetry here, but what would happen if we rotate it? Let's see. And stop, right? So notice here that we actually have 1, 2, 3, 4, 5, 6 parts, right? 6. And if we thought about it in terms of being a polygon, if we connected like the tips of these triangles, here we would have a hexagon, right? We would have a 6-sided. So we just rotated it a sixth of the full rotation, and a sixth of 360 degrees is 60 degrees. So we have 60-degree turn symmetry, but also again, because of the regularity of this shape here, we could turn it 120 or 180 or 240 or 300, and those would all be turn symmetries also. Again, we do not include 360 degrees as a turn symmetry because all shapes would have turn symmetry of 360 degrees because that's its original self. So we only include those less than 360. What about this shape here? Well, it looks like if we completely flip it upside down, we get the same shape, which means we have 180-degree turn symmetry. Okay, and again, there's not any others besides that one because of this, it doesn't have anything less than another complete rotation, right? So you have to remember not to include the 360 degrees. So with the rotational symmetry of 180 degrees, we actually can say it has a special kind of symmetry. So any figure that has rotational symmetry of 180 degrees is said to have point symmetry about its turn center, right? About the point at which you turn it, right? So all of these shapes, if you flip them upside down, if you rotate them 180 degrees, they're going to be exactly the same. So all of these shapes here have point symmetry about their turn center, and their turn center is the red point labeled there. I didn't animate these ones, but I think you can see that when you turn them 180 degrees, they'll be the same. Also remember that this is saying I'm turning 180 degrees positively, which should denote the counterclockwise direction. But of course, rotating negative 180 degrees or the clockwise direction would produce the same result. So we can actually classify geometric figures based on the kinds and numbers of symmetries that they have. We can use lines of symmetry, and if they have, and what kind of turn symmetries they have, to define various types of quadrilaterals and triangles that we normally use in geometry. So let's consider an example. Consider a triangle described as having exactly one line of symmetry and no turn symmetries. What would we have? So the only possibility, quite honestly, is a triangle that has exactly two sides being congruent. The reason we have to have exactly two sides being congruent is because we have one line of symmetry and no turn symmetry. So let's see what this would look like. One line of symmetry. So if we have one line of symmetry, that would allow us to fold or reflect this left part across to the right part or vice versa, which means I have these two sides, AB and BC, being congruent. So that gives us exactly two sides being congruent. The reason we can't have all three sides being congruent is because if this last side, AC, was congruent to AB and BC, then we would have a turn symmetry, right? We would be able to have 120-degree turn symmetry because we would have an equilateral triangle, right? So notice that we were able to say we have an isosceles triangle based on just knowing we have one line of symmetry and no turn symmetries. Okay, that finishes up 11.3. We'll move on to 11.4.